Okay, I think maybe we should start. So it's my pleasure to introduce our guest speaker today, Jonathan Deroux from University of Basel. He just recently started his tenure track assistant professorship in September. Giving a little bit of background, so he's Belgian. So he did his early studies at Ghent, did his PhD there with Zeger Hens, among others. So he knows well, apparently, Peter Geigerat, who we just had a few weeks ago. He then, well, during his PhD, he spent a few months here at ETH, actually, working with Maxime Kovalenko and Marcus Niederberger. And then he did his postdoc at Columbia, which is when he overlapped with Andrew. And there he worked with Jonathan Owen. And then he went back to Ghent briefly, I guess for like a mini postdoc before he started his position at Basel. And as you can see on the screen, he's going to talk to us about the surface chemistry of colloidal nanocrystals empowered by NMR. So go ahead, Jonathan.
Thank you. Good afternoon, everybody. Welcome to this, my first Zoom seminar, actually. We're going to talk about the surface chemistry of colloidal nanocrystals. And really, the beating heart of that research is NMR. So this line here that just appeared was not a human beating heart, of course. It would be a very unhealthy person. This is an NMR spectrum of bound ligands. And as a quick reminder to everybody that probably you don't need it, but we're going to do it anyway. A nanocrystal is an organic, inorganic hybrid object. So in TEM, you see this inorganic part of it, but on the surface, there is a layer of organic surfactants around it. And the way that these are bound to the surface, this is the subject of surface chemistry, and that's what we are going to talk about today. So we have TEM to look at the inorganic part, but we also need a tool to look at this organic part. And for that, we have NMR. And we have a couple of different techniques in NMR. First, there is a very simple 1D, it's the most basic experiment that you can do. But it already tells you something about the bound state of a certain molecule, because free molecules have this sharp peaks with fine structure, while bound molecules have broadened resonances. The second NMR technique that we can use is diffusion ordered spectroscopy. And that's because a free ligand diffuses rapidly in solution, while when it's bound to the nanocrystal, then it has to move with the big nanocrystal and it diffuses much more slowly. The third technique that we have is nuclear Overhauser effect spectroscopy. And that's actually a complicated technique from the theory point of view, but we don't need the theory. The only thing that we need right now is to know that a free ligand gives us these red cross peaks and a bound ligand gives us these black cross peaks. So there's just the sign of the cross peak that will tell us whether a molecule is bound or not. So the theory of NOESY and its relation to nanocrystal surface chemistry is well established, as is DOSY. It's very easy to understand. What is, or what was a bit more contentious is this line broadening and the origin of that. So the first section of this talk will actually be about that, the origin of this line broadening and how it is connected to the heterogeneity at the surface. Then in the second part, we'll talk about the non-innocence of solvents and how this can contaminate our sample. And in the last part, we'll talk about surface chemistry on demand, which means that we will synthesize new molecules, new ligands that will enable certain applications. But first to the line broadening. So this is a very typical spectrum that you will see many, many times over in this presentation. So this is a 1D spectrum of oleate cap nanocrystals. So maybe important to say that those were 3.3 nanometer nanocrystals. And so you see these broadened resonances. This is resonance 5, which is the double bond, the alkene resonance. 6 is the methyl resonance. 3 are all these CH2s in between. 4 are the ones next to the alkene. And then 1 and 2 are these very, very broad resonances here that are attached to the nanocrystal. Now, there are two ways of broadening in NMR. The first one is homogeneous broadening. Homogeneous broadening depends on the T2 relaxation. And that actually depends on the rotational mobility of a certain resonance. So molecules with very high rotational mobility have narrow lines. Molecules with low rotational mobility have broad lines. But that's actually something that we can measure, the T2 relaxation time. So that's what we did. First, what we established is with a diffusion ordered spectroscopy experiment that the ligands were tightly bound to the nanocrystal surface. That's important because we want to gain information of the bound state, not of a free state. Then here is the full width at half maximum of resonances 5 and 6. So this alkene resonance and this methyl resonance, because they are nicely isolated from the other resonances. And you see that the alkene resonance is more broadened than the methyl resonance. This completely agrees with this concept of homogeneous broadening, because the resonances very close to the surface are more static. So those moieties do not have much rotational mobility, while the methyl resonance, which is completely at the other end, it's at the end of a floppy chain, so it has a lot of mobility, and that's why its full width at half maximum is a lot lower. And indeed, that's also reflected in our T2 measurement times. And from the T2 time, we can calculate the homogeneous broadening according to this very simple formula. And then you see, indeed, this is what you expect. According to the T2 times, the alkene resonance should be broader than the methyl resonance. Okay. But compare now this calculated homogeneous broadening with what we see experimentally. And then you clearly see there's a disconnect. There is a lot more broadening going on than predicted by this homogeneous broadening. And that gap is filled up by heterogeneous broadening, which means that this single resonance here is not a single resonance that is nicely homogeneously broadened. Instead, it is a superposition of all kinds of different resonances which each of its resonance has its own broadening. You can get in such a situation when all those different resonances have slightly different chemical environments. And then now is the question, where do those different chemical environments come from? And so we argue that they actually depend mostly on the solvation or the unsolvation of the ligand shell. And to prove that, we needed a model system that would allow us to look at the line width in many different solvents. And then this oleal chain is not really suited because it gives us solubility in hexane and chloroform, but not really in polar solvents. And so we turn to this particular ligand. It's a mouthful when you want to say its real name, which is methoxyacetic acid. I usually call it MEA. And this molecule allows us to disperse both oxides and selenite nanocrystals in a variety of solvents. So here we show the NMR spectra of hafnium oxide that is capped with this particular molecule in water, methanol, ethanol, acetone, and toluene. And you see that this line width clearly depends on the solvent. So the solvent has something to do with it. Now, some critics might say that the solvent can also influence the homogeneous broadening through its viscosity, and that's correct. But if we plot now this full width at half maximum in function of the solvent viscosity, you don't see any correlation. If any, you would think there is a negative correlation, which is not what is predicted for homogeneous broadening. You should see then an increased full width at half maximum with an increased viscosity. So viscosity has nothing to do with this trend in line broadening. But if you plot the line broadening in function of the Hansen solubility parameters, then you get a really, really nice correlation if you use the hydrogen bonding parameter. So Hansen defines 3 different parameters. One was the dispersion, one was the hydrogen bonding, and one was a polarity index. And it turns out that this data correlates best with the hydrogen bonding parameter. And this is not very surprising. Just look at this molecule. This really likes hydrogen bonding. So any solvent that is very good at hydrogen bonding would interact really well with this particular molecule. And so water is the best, then methanol, ethanol, then acetone, and then toluene. So from this, we concluded that the NMR line width of a bound ligand depends on the solvation of the ligand shell. When a certain ligand is very well solvated, it is completely surrounded by solvent. That means it has a uniform environment, and thus there is a limited heterogeneous broadening. But when solvent is excluded from the ligand shell, for example, here in toluene, which does not interact really well with this chain, in that case, all the chains come together and interact with each other, and then they don't have a uniform environment, leading to heterogeneous broadening. Now, we try to confirm this with molecular dynamics situations and simulations, and there is a lot to be learned from these. So we started out with this particular situation where all the ligands were fully stretched out. And what is immediately apparent if you let this calculation go, it doesn't matter which solvent that you use, but those ligands twist and turn. So this is pervasive in the literature, that everybody draws their ligands as like a straight rod, and even oleic acid they draw as a straight rod, even though it's impossible for oleic acid even to do that because it has this double bond. So this is the first takeaway home message here, that indeed these ligands twist and turn, and they have a more complicated configuration. Now, their extension, so how far they are extended in space, that depends on the solvent. So in methanol, in which the ligand shell is much more swollen, they're a lot further extended than, for example, in toluene. So this is what we propose, that the line width depends on the solvation of the ligand shell. And these molecular dynamic situations seem to confirm that. So now that we have a theory, we can go back to the case of oleic acid ligands and see with this new pair of glasses that we have if we can understand the data there. And here we have the alkene resonance. So we're going to zoom in only on the resonance of the double bond and focus on that. So we did this for quetzalnite, lead sulfide, and hafnium oxide. And then you see that in toluene or in any other aromatic solvent, there is a big difference between the chemical shift of the bound state and of the free state. Now, there is such a thing in aromatic solvents as the aromatic solvent-induced shift, meaning that an aromatic solvent causes all the resonances to shift in a certain direction, and with respect to an aliphatic solvent. So now you can understand this shift here because of solvent exclusion. In a free oleic acid molecule, which is completely surrounded by an aromatic solvent, fully experiences that induced shift. While the bound ligands, they're not fully surrounded with aromatic solvent, they feel each other, so they are in a partly aliphatic environment. And so this supports again this hypothesis of solvent exclusion from the ligand shell. So that was a neat piece of data that we didn't understand for a very long time. Why was there such a shift in aromatic solvents, but not in solvents like chloroform? So in chloroform, there is a narrower line width. That's already what when you compare the same nanocrystals here, quetzalnite is 70 Hertz in toluene, 50 Hertz in chloroform. In light of our theory, this means that chloroform is better at solvating that ligand shell than toluene. And this has been already reported in literature by people that do these assemblies of nanocrystals. Now, what is now the best solvent for an aliphatic chain that's another aliphatic molecule? And so if you take here this alkene resonance in toluene, which is quite broad, and then you add hexane to this solution, then you get extremely, extremely narrow resonances. And that's because hexane is just the best solvent possible for this aliphatic chain. Okay, so now we understand that the line width depends on the solvation. And how does it depend on the size of the nanocrystal? And so here you see different sizes of lead sulfide nanocrystals. And again, the alkene resonance. We always focus on the alkene resonance because it's so nicely separated from all the other signals. And so you clearly see that the line width is dramatically increasing actually with the size. And we disentangled, again, the contributions into a homogeneous broadening and a heterogeneous broadening. And then you see something very curious. The homogeneous broadening is always increasing, and that is logical, because the homogeneous broadening depends on T2 and thus on the tumbling. When you have a bigger object, you get slower tumbling and the more T2 relaxation. So this is exactly what it should be. You should see a continuous increase in the homogeneous broadening. On the other hand, the heterogeneous broadening is quite high and takes up the biggest part in small nanocrystals, about 3.5 nanometers. The biggest part of the broadening is heterogeneous broadening. But as soon as you increase the size, at some point this heterogeneous broadening levels off to a constant value and then doesn't increase anymore. And that's actually because of surface curvature. Because small nanocrystals have some curvature and a lot of solvent can penetrate in between the ligands. But as soon as the nanocrystals grow and the curvature decreases, or they become faceted, and then you even have flat surfaces with no curvature, then you push all the ligands closer to each other and then further increasing the size will not influence this heterogeneous broadening anymore. So that's again how you can interpret that. That was one part of broadening, one part of heterogeneity. But there are many different aspects of heterogeneity in nanocrystals. The one that you're probably most familiar with is just the nanocrystal core. There's a dispersity in your nanocrystal ensemble. There are not many nanocrystals that are with exactly the same number of atoms. And from UV-Vis and from TEM, you can assess that. You can put a polydispersity number on your core. So that's actually already heterogeneity. Then what we just talked about is heterogeneity of solvation of the ligand shell. And that's something that we can probe with the NMR line width. But there is something in the middle here, which is actually the binding of the ligands to the nanocrystal. And that also has heterogeneity associated with it. But it's very hard to actually get information on that. And that's what we're going to do right now. But before we do that, I have to introduce a little bit of the language that we need to talk about surfaces. So Green introduced this LXZ covalent bond classification to classify ligands. And so here we have a Lewis base, Z-type is a Lewis acid, X-type donates, in the official definition, donates 1 electron to the nanocrystal bond in its neutral form. And this is very useful to distinguish interactions of ligands to nanocrystals. For example, when you say oleic acid binds to the nanocrystal surface. Well, then how does it actually bind? It could bind as an X-type ligand, but this second L-type interaction can also happen, and then this is an L-X-type ligand. Or oleic acid as such, not as oleate, but as oleic acid, can also bind in an L2 fashion. But unfortunately, we don't have the spectroscopic tools to distinguish those configurations, so we usually call oleic acid an X-type ligand. Then another model that is often used in organometallic chemistry is just the ionic model, where you separate the ligands and the metal based on oxidation states. And then you have ligands that are Lewis bases, neutral Lewis bases, or charged Lewis bases, or you have neutral Lewis acids or charged Lewis acids. And so both models can be used to talk about surfaces. Then one thing is just the interaction of one ligand to the nanocrystal. Another thing is to combine the type of interaction with the stoichiometry of the nanocrystal. And since we work mostly in nonpolar solvents, at least during the synthesis, we can apply the charge neutrality principle that the whole unit, the whole nanocrystal ligand unit needs to be charge neutral. And then there are not many options. Then there are actually only 4 binding motifs. and 2 of them are even equivalent. So you have this one where you have excess of cations on the surface. Cations are green, anions are red. Those excess of cations need to be charge balanced with X-type ligands. In the ionic model, this is a bit more clear that there is a cation and a charge balance here. So this one was originally introduced by Owen, and he recognized that this was actually the same as a neutral nanocrystal with a Z-type ligand. So it just depends where you assign this particular metal cation. Do you think it's part of the surface? Do you think it's part of the nanocrystal core? Or do you think it's part of the ligand? If you think it's part of the ligand, then you call this cadmium carboxylate a Z-type ligand. If you think it's part of the nanocrystal, then it's a cation-rich nanocrystal with X-type ligands. This is conceptually the easiest one, a neutral nanocrystal with a neutral L-type ligand, so a Lewis base. This is the one that we introduced for metal oxides, where carboxylic acids can dissociate, and you have 2 X-type ligands. One is the proton binding to an oxygen, and the other one can be the carboxylate binding, or a chloride binding to the metal. Then there was also the cesium-lead bromides who can be classified in the same class. It's harder to assign to say that this ammonium is an X-type ligand because it's more like a hydrogen bonding interaction or a purely ionic interaction and not really a covalent interaction. So it's maybe safer to call it, to describe it in the ionic model, where you just say it's an ion pair that is binding both to the surface. So both ions are binding to the surface. So this whole classification of binding motifs is very useful because it allows you to talk about ligand exchange and to concisely write down what is happening. And so there are really easy ligand exchanges like an L for an L or an X for an X, but this is the one that we will need today. And this is the L-type promoted Z-type displacement. This is where you will desorb this entire Z-type moiety by L-type ligands. This forms a Lewis acid base adduct. And this is actually the driving force for this displacement. And that's exactly the one that we are going to use to look at the heterogeneity of the binding of ligands to the surface. So this is the experiment that we did. We started from cadmium selenide capped with cadmium oleate, and then we add an L-type ligand. And we did this for 3 different L-type ligands: butylamine, benzylamine, and TMEDA. This is tetramethyl-ethylene diamine. So this can bind in a bidentate fashion, and this is monodentate. And so you see that when we add an L-type ligand, you see this second peak appear. So this is the free, and this is the bound. And now if you fit those two, you can disentangle the 2 contributions, and you can say what is the fraction bound and what is the fraction free. We do this for many different concentrations, and that gives you an isotherm. So the fraction of bound ligands in function of the L-type concentration. And if we want to do thermodynamics, the first thing that you have to know is the chemical reaction and the stoichiometry of that chemical reaction. So in order to find that out, we did a dilution experiment, because if the number of units of the number of species left and right of this equilibrium, this should actually be an equilibrium arrow. If the number of units left and right is the same, the equilibrium constant will not change with dilution. The equilibrium constant will never change. The speciation will not change with dilution. But if there are more units on the left-hand side than on the right-hand side, then the reaction will be forced to the left when you dilute. And this is exactly what is happening for butylamine and benzylamine. So this tells you here that actually TMEDA is binding in this bidentate fashion, where these 2 L-type moieties are linked together in TMEDA. So there are 2 units to the left and 2 units to the right. And so now we have an expression for the chemical reaction. So we can write down the equilibrium constant, and we can fit this data to a certain equilibrium constant. And if you try to do that, you actually fail. And so you cannot describe the data with a single equilibrium constant. You have to introduce at least 2 equilibrium constants that yield an isotherm that describes the data. So there is a fraction of ligands that is really loosely bound, that are easily desorbed from the surface. And there is a fraction that is more tightly bound and that are more difficult to desorb from the surface. So we roughly divide it in two categories, but it's actually much more complicated than that. And Ivan Infante did some calculations on this. He made an entire nanocrystal capped with Z-type ligands. And then on this particular facet, he removed the Z-type ligand from many different locations. And what he sees is that the desorption energy varies wildly based on where you take the Z-type ligand away. So this clearly illustrates the heterogeneity of the nanocrystal surface in terms of binding affinities. So there is not one single binding affinity. So it's very deceiving when you write something like this, where we represent all possible, and there's hundreds of binding sites on this Quetzalite nanocrystal, but we represent it with this single one. And we present this reaction as if it is governed by a single equilibrium constant, which it is clearly not. This is even more clearly exemplified with nanoplatelets, which have those flat facets, and there are also the edges around the platelets. And this is translated in the isotherm. So when you look again at the bound fraction of oleate in function of the L-type ligand that you titrate in, there is a fraction that desorbs rapidly, which is associated with the edges of the nanoplatelet. And then there's a very, very large fraction that is very hard to desorb. And that's associated with the middle of the flat part of the platelet. And it has also a very dramatic effect on the quantum yield. So these edges, if you desorb there the cadmium oleate, then you destroy your quantum yield very, very quickly. And recently, Zeger-Hens worked further on this and made core crown platelets and showed that then when you have a core crown, you can actually desorb some of the ligands on the crown and it doesn't influence your quantum yield. So that was also very neat. Okay, so that was the first part. I talked about heterogeneity on the surface on two different levels, one of the binding affinity and one of the solvation of the ligand shell. So let's pause for 5 seconds. And then we're ready for the second part of the talk, which is the non-innocence of solvents. And I just want to reach out to you students that have not forgotten how it is to be in the lab and to try to take a TEM of your nanocrystals. And so it's very hard in the sense that you have to clean your nanocrystals really well, because otherwise if you go to the TEM, you get a lot of burning. And so if you move the beam, you see that you actually have made a big black circle where you were before. And people often, I hear people often describe this as organics. Oh, there are organics in your sample. And the question is, what is the name of this suspicious and elusive organics? And that name is polymerized octadecene, because that is a very popular solvent. And we actually found that it polymerizes during the reaction. So here we did an experiment where we just heated up octadecene without anything. So no, there is no catalyst in there. And as soon as you're at 120 degrees, it starts polymerizing. So the rate is really low. But at 320 degrees, which is the boiling point of octadecene, and which it's a temperature that's often used for nanocrystal synthesis, there you convert to almost 100% yield in 24 hours. So that's a really substantial rate of polymerization. The molecular weight of the polymer that you form is a little bit temperature dependent, and you can look at it through diffusion ordered spectroscopy. Because again, you have now a bigger object that diffuses slower than the octadecene molecule itself. So that's what you see here. Chloroform, a very small molecule, diffuses very rapidly. Octadecene is a bit bigger, diffuses slower, but even a lot slower is polymerized octadecene. You can see this in the DOSI, but you can also see this in your 1D spectrum. If you have giant peaks here between 1 and 1.5 ppm, then those peaks are probably oxidation. So, okay, you say all kinds of things are happening in my reaction. Why is it so bad that there is a bit of polymerization of oxidation? Well, that polymer looks a lot like your nanocrystal. It has similar size, it has similar solubility because your nanocrystals are capped with hydrophobic ligands. The polymer that you make is hydrophobic. Like a polymer that is bigger in size than a molecule, and it approaches the size of the nanocrystals. It's not exactly the same. It's still a bit smaller, but still. So it's very hard to now separate this polymer impurity from the nanocrystals. What are typical methods to purify nanocrystals? Precipitation with a polar solvent. That's not going to work because the solubility is the same. Or gel permeation chromatography, where you try to separate based on size. But the cutoff is quite low, and both the polymer and the nanocrystal go through the gel without any problem. We tried that. I have to be honest that we're not specialists in GPC chromatography, so maybe we did something wrong, and it is possible if you're really, really careful about this. But so in our hands, it did not work to separate it based on size. What is interesting to note is that the solubility of this polymerized octadecene is more or less okay, or is higher in methyl acetate. You can still precipitate it with methyl acetate, but you precipitate less if you use methyl acetate. The solubility is a bit lower in isopropanol. It's a lot lower in ethanol and acetone, and it doesn't mix at all with acetonitrile and methanol. So this gives you also an idea if you really want to use ODE and you want to purify the polymer out at some point, that methyl acetate is your best shot of doing so. Is this a widespread problem? Yes. We have found this in at least 5 different nanocrystal syntheses, and some of them are oxides, some of them are sulfides, so it ranges widely, and we have detected polymerized octadecene using DOSI in all those 5 samples. And then, what's now the solution? So I presented you with a big problem, like many nanocrystal samples are contaminated with polymerized octadecene. How to deal with this? Well, one of the obvious answers is don't use octadecene. Use another high boiling solvent, such as octadecane, or hexadecane, or squalane. Those are all good options. And in many cases that works. So, oh, I skipped this. Well, let's go directly here. In many cases that actually works. You can get exactly the same nanocrystals as you got before, but this time without polymerized octadecene. That is, if your nanocrystal reaction depends on some precursor chemistry that's controlled. And the solvent should be there as an inert heat transfer medium. But in some cases, like the case here of zinc sulfide that's doped with manganese, there the reaction actually relied on octadecene to reduce sulfur to sulfur 2-. And of course, there you're messing with the chemistry of the reaction if you change the solvent, and you get poor particles. And the previous slide here was just to show you of how big of a problem this is. So we listed the 5 different syntheses that we explored, and how much of polymerization do we actually expect at the end of that reaction, because most reactions do not take 24 hours. And then you see that we still get an appreciable amount of polymerization. It's not 10 or 50% of polymerization, but you don't need a very high conversion to make your life hard, because this is the solvent. It is present in a huge amount. So even 3% of conversion, 3% of polymerization, that gives you a big problem in your nanocrystal purity at the end. So one way of dealing with this was just using alkane solvents. Right? Don't use double bonds. The second way around this is change the polarity of the nanocrystals. So if you really want to work in octadecene, and afterwards you want to separate the polymerized octadecene from your nanocrystals, you have to change the polarity of your nanocrystals. And in this case, we did this by using phosphonic acids. So both Hens and Dempsey showed that this is not an equilibrium, that if a phosphonic acid is added to a carboxylic acid bound to a nanocrystal surface, this reaction goes through completely, will displace the carboxylate, and the phosphonic acid will bind, which means you only need one equivalent. So this is a very economic exchange. So this is what we did here, and here you see the NMRs. The red is before the exchange, so you see a little signal of oleate, and then you see these two huge peaks of polymerized octadecene. So then we exchanged it for this phosphonic acid that's slightly more polar. This PEG, as we have seen before, is quite versatile. So the nanocrystals remain soluble in chloroform, but if we now add hexane, they precipitate. But the polymerized octadecene, that is still soluble in hexane. So that's a way of separating now polymerized octadecene from the slightly more polar nanocrystals. And the result after purification you see here. So these peaks belong to the little PEG chain, and then those peaks here belong to the aliphatic chain. And what is very notable is that you don't see this polymerized octadecene anymore. So that was one very popular solvent which has a huge problem. There are more solvents in nanocrystal synthesis that are problematic. And one of them is topo, trioctyl phosphine oxide. And it was already shown by Bill Burrow in 2008 that commercial batches of topo contain many, many impurities. And those impurities are actually relevant because especially those phosphonic acids and phosphinic acids, they bind to the nanocrystal surface and could direct growth. For example, make rods. Then John Owen showed that you can recrystallize topo in such a way that you get pure topo and you can eliminate all those impurities. So that's also what my lab is currently doing. We're always recrystallizing the commercial topo that we're getting. And we really like oxides. So we make oxides in topo from zirconium chloride and zirconium isopropoxide at 340 degrees. It's quite high temperature. And we get these beautiful zirconium oxide nanocrystals. They're very monodisperse. And when we look in the proton NMR spectrum, they look pretty nice. So we have nicely purified them. We see two peaks, a methyl and some ethyl moieties that agree with what everybody thinks, which is that topo, this trioctyl phosphine oxide, is not just a solvent, but it's also the surfactant. It's binding to the surface. And this is a very useful way of synthesizing nanocrystals. And people have not only done this for zirconia, but also for titanium oxide, hafnium oxide. So it's an important synthesis out there, and many people that need hafnium oxide actually make it in this way. But everybody assumes that topo is bound to the surface. And so the one way of finding that out is take a phosphorus NMR spectrum. And you remember that the closer you are to the surface, the broader the lines. And of course, the phosphorus is part of the binding group. So that's very close to the surface and the lines are very broad. But if you measure for hours, you can still get a decent spectrum. And this is what we got when we investigated the zirconia nanocrystals. And what did we expect? If we expected topo to be bound to the surface, then we would have expected here one single peak in the phosphorus spectrum. We don't see that. We see three different peaks in toluene. And in chloroform, we even see a fourth. And that actually means, if you look here at the intensities, that this particular peak decreased in chloroform and this particular peak appeared. Now that was very helpful to us because this one matches with the chemical shift of topo itself. So this one here is protonated / hydrogen bonded topo to the surface. And then it took us a long time to figure it out, but in the end, after a lot of control experiments, we figured out that these two molecules are dioctyl phosphinic acid, and this is the anhydride of octyl phosphonic acid. So topo is actually decomposing during the reaction into these impurities that bind very strongly to the surface. I should also say that, well, we have here a positive charge, and this is balanced by chloride. So there actually, you can also think of this as hydrogen chloride on the surface, and then topo being hydrogen bonded to it. So this is a very complex surface chemistry. And for any application, that's undesired. And so we want to clean this up a little bit. And we tried this with carboxylic acids, and that works to some extent, but the best results we get when we use other phosphonic acids, like octadecyl phosphonic acid. So when we add ODPA, so octadecyl phosphonic acid, we are able to displace all the original ligands. So that HCl is gone, topo is gone, dioctyl phosphonic acid, and the anhydride, it's all gone. And we have one nice peak in the phosphorus spectrum. And this is a very beautifully purified nanocrystal dispersion. You don't see anything except for toluene and then this alkyl chain. So that's a way of cleaning up the mess that the decomposition of topo caused. Okay, that was part 2. So solvents are non-innocent, and octadecene is polymerizing, topo is decomposing, and both phenomena are actually leading to contamination of your final product. Now we're gonna go to surface chemistry on demand, where we will make our own ligands based on, actually this was inspired by trying to find a ligand that binds really well to the surface, to design the ideal ligand. And the first thing that you remember from the previous part of the talk is that phosphonic acids are really good ones. They are really good ligands. And so we looked around and we saw that all people in the literature are actually using octadecyl phosphonic acid, tetradecyl phosphonic acid, those fully saturated ones, but they're not very nice to work with. They're very insoluble. And so we identified a couple of phosphonic acids that we thought would be really useful for the nanocrystal community. And those are here, drawn. So there is the octadecyl phosphonic acid. This was just our baseline. Then very surprisingly, nobody is using oleophosphonic acid. Well, it's not surprising since it's not commercially available. And we're not really a community that does a lot of organic synthesis. So, well, people prefer to buy this molecule than try to synthesize this one. But so we showed how to do it, and it's actually not very difficult. Then we already know that this PEG molecule is very useful. So we also wanted to synthesize a phosphonic acid version of this. And then there was this very intriguing contribution of Peng and Nanoletters, where there were 2 back-to-back papers describing entropic ligands with these branched ligands that have a higher solubility than their straight chain counterparts. And those ones that give better solubility, and we thought, okay, it would be useful to have those as phosphonic acids too. The way that we do this is depicted here. So often we have to start from the alcohol when there is no bromide substrate available. In that case, we use the Appel reaction to convert the alcohol into bromide. Then we have 2 options. There's either Michaelis-Becker or the Michaelis-Arbusov to make the phosphonic acid ethyl ester. The Becker is done at room temperature, where you deprotonate diethyl phosphide and then attack the bromide. And the Arbusov reaction is where you start from triethyl phosphide and you heat this up with the bromide. Problem with this one is that you form ethyl bromide as an impurity, as a byproduct, and that can actually also react with triethyl phosphide, giving you an ethyl phosphonic acid impurity. This one, the Arbusov reaction, does not work for these more sterically demanding substrates, 1 and 2. So 1, 2, 4, and 5, we synthesized using the Becker method, and for some reasons didn't work with 3, so there we used the Arbusov method. And then the ester is easily hydrolyzed into the phosphonic acid. Now, in case of 5, this crystallizes really well, and we made very high quality crystals in large amounts. So you can make multiple grams of this without a problem. That will last for a very long time because we don't use that much ligands anyway. And so this was high enough quality for single crystal, and then you could see the hydrogen bonding network. So that was kind of fun. Then we have to test how well do they bind to the surface. Well, we know phosphonic acids bind really well. But what we also know is that sterically hindered ligands, or very sterically demanding ligands, are not so favorable to bind to the surface. So that was shown by John Owen and by Zegerhead for L and X type ligands both. So here we said, okay, let's start with this ligand 1, which is branched, so it's slightly sterically hindered, and see whether we can do this quantitative exchange. And the answer is yes. And so you start here in the green from oleic acid capped nanocrystals, quetzalnite, and you add one equivalent of this 2-ethyl hexyl phosphonic acid, and immediately you see this beautiful pattern of the double bond, which means that oleic acid is completely free in solution. It's not interacting at all with the nanocrystal surface. So then you purify this dispersion, and this is what you end up with. You see one peak in the phosphorus spectrum. You see the peaks in the proton spectrum belonging to this molecule, and you don't see the oleic acid signals. And so this also works for the other phosphonic acids. And one in particular is very useful because now we have oleal phosphonic acids. You will have noticed that I always talk about oleic acid because it has this very useful resonance at 5.5 ppm. But now we have oleal phosphonic acid. So now we can look at phosphonic acids in NMR and do some more detailed analysis. And let's return now back to this Z-type displacement. So here we displace again this cadmium carboxylate or cadmium phosphonate with TMEDA. So we use tetramethyl ethylene diamine. And to my very surprise, this gave exactly the same isotherm. So we know phosphonic acids bind stronger than carboxylic acids. We might also expect that cadmium phosphonate binds in a different way than cadmium oleate. But still you get exactly the same isotherm, which, if you think about this, is actually logical. Because what you're probing here in this experiment is not really the affinity between the nanocrystal and the Z-type ligand. It's more the affinity with the L-type ligand. Because look at this. So here you have, well, I will say this differently. Let's say you have a much stronger Lewis acid, this cadmium X2. For some reason, it's much stronger. Then you would expect it to interact more strongly with quetzalnite. But you would also expect it to interact more strongly with this L-type ligand. So there is both an energy gain on the left-hand side and on the right-hand side of this equation. So those two things balance each other out. Does this mean that cadmium oleate and cadmium phosphonate have an equal binding affinity to the surface? No, I don't dare to say that. I think if you want to know that, you have to do this desorption experiment without extra ligands, but purely thermally activated, and see which one desorbs first when you increase the temperature. What this data does tell you is that a phosphonate does not protect you, it does not protect the nanocrystal from desorption by L-type ligands. So this is my interpretation of this data. I have to say this does not have the stamp of approval of Jonathan Owen. This was my postdoc advisor, and this was the one time where we really fought, staring at each other across the table and mumbling and rumbling, and nobody wanted to cave, but in the end I had to cave. So this did not make the final manuscript, but I want to share it here because I really believe in this data. Then we don't only did quetzalnite with these phosphonic acid, but we also combined it with hafnium oxide. And so we took our whole little series of phosphonic acids and we functionalized hafnium oxide with it. And by doing that, well, we had shorter ligands, we had longer ligands. You can actually tune this interparticle distance. So with ligand 1, oh, this is wrong. Ligand 1, no, this is ODPA. So this is oxidizylphosphonic acid. It is 2.4 nanometers, the interparticle distance. And with ligand, the 2-ethylhexylphosphonic acid, it was 1.6 nanometers. Now, how was this useful? Because we wanted to use hafnium oxide nanocrystals in memory sticks, so in novel memory devices. The way that works is that you assemble those nanocrystals in little ribbons on a conductive substrate, and now you can switch those ribbons between two states, high resistance and a low resistance state. And that's basically the 0 and the 1 that you need for memory. Now you want that switching happens with a voltage. You want to have that voltage quite low, because otherwise you're using a lot of energy to switch between the two states. And what we see is that the switching voltage that you need really depends on the ligands that you put on the nanocrystal surface. So these very long oleal or octadecyl ligands need very high switching voltages, while those branched ligands, the 2-ethylhexylphosphonic acid, for example, gives you a very low switching voltage of only 1 volt. And so this is very useful because we're competing here with vacuum technologies that are making these hafnium oxide memristors. And here we present a solution-based process where we just have the nanocrystals and we deposit them on a substrate, just like that. Or we can even print these things if we want to. So this is a lot cheaper than the vacuum technology. And it's very important for us to keep both the voltage low, but to also keep the solution processability. And that's why those branched ligands really shine, because if you would just take hexylphosphonic acid, the particles precipitate. But if you take 2-hexylphosphonic acid, the particles remain in solution, but the ligand shell did not increase. And it also allows for this low switching voltage between the two. So 2-ethylhexylphosphonic acid gives you the perfect combination of solution processability and at the same time a low switching voltage. Now you can ask yourself the question, what is better than 1-phosphonic acid? And that's, of course, 2-phosphonic acid. So in our quest to find the best binding ligand, we designed this particular moiety here, this particular ligand, with 2-phosphoric acid, at a certain distance that we thought would be useful. So we synthesized this molecule. Let me check the time. I will not discuss the synthesis. So we synthesized 3 different versions with 3 different substituents here are. And then you have watched this presentation for long enough to know what's going to come. And that is an NMR experiment showing the exchange, of course. And here we want to show that it really binds in a bidentate fashion, so that you can exchange 2 oleic acid ligands for 1 of these diphosphoric acid ligands. And that actually works. If you add only 0.5 equivalents of this ADP anthracene diphosphoric acid ligand, then you can strip all the oleic acid from the surface. And you see that the alkene resonance has disappeared. You see 1, that's important, 1 peak in the phosphorus spectrum, which means that those 2 have about the same chemical environment. So 1 is not free and the other is bound. No, they're both bound. And we can keep the nanocrystal in solution with this particular ligand. And we used, these are very curious looking ligands, these anthracene ligands, but they're actually useful in upconversion. And the one with the phenyl is actually the best ligand for that. So here we combined our new ligand with Kitsan-like nanocrystals to create 430 nanometer photons from 488 nanometer photons. So the nanocrystal absorbs as photon and creates a singlet state. There's intersystem crossing to a triplet state. That triplet state is transmitted to this transmitter ligand, it's called, and then this ligand transmits it to the diphenyl anthracene in solution, which actually does the upconversion. And if you do that with our ligand, you get 17% upconversion quantum yield. If you do that with the standard that people are using in the field, you get 30%. So we got like a record high quantum yield in this system. We've initially thought this would be because the ligand was just binding better to the surface. That did not turn out to be true because the rate of triplet transfer from the nanocrystal to the ligand was about the same. What was very different is that this one has a higher photoluminescence quantum yield, and a longer triplet lifetime. So the triplet survived longer on this ligand, so it had more time to transfer to the diphenyl anthracene. Okay, those were two different applications where we tailored the surface chemistry to their application. And I want to conclude, but first I'm going to show you one slide just about what we're doing currently in the lab. So we're still working on nanocrystals, mostly oxides, and we're also interested in oxo clusters. Those clusters are the building blocks in MOFs and also are used for 3D printing. And so we're investigating those. And we're also using X-ray total scattering to get a better look of the nanocrystal core. So we really want to combine our surface characterization methods with a more detailed view of the nanocrystal core, and then gain a better understanding of the total structure of these nanocrystals. So you typically do this at the synchrotron, but we will have a lab source instrument installed in July so that we can do this much more regularly. Now, really, in conclusion, what did I tell you today? I told you that the surface is a very heterogeneous place. So the NMR line width is broad because of incomplete solvation of these ligands. At the same time, also the binding affinity is not unique, but there is a whole range of binding affinities. Second, solvents are non-innocent. Octadecene polymerizes, topo decomposes both Colloidal troubles and impurities in your final nanocrystal product. Then finally, we did some surface chemistry on demand where we showed how to synthesize new ligands that would be useful for the nanocrystal community. We applied them in memristors and in upconversion. And if you look now at this whole summary, then it must occur to you that all this was enabled by NMR spectroscopy. And with that, I thank you very much for your attention. And those were all the people that also contributed to this work. And of course, the funding agencies. Thanks a lot.
Thank you. So what I suggest now for questions is if you use the raise your hand feature in Zoom, and then I'll try to call anyone I see here that raised their hand. So first up, I guess, is Marianne.
Hi, thank you for your talk. It's really interesting. I have a question on the first part of your talk. So I'm not really very familiar with NMR, but I was wondering, so you're showing these graphs of the different nanocrystals. So you have different lines of various nanocrystals, and then this reference line of the oleic acid in a given solvent.
This one, for example.
It was basically about where you compared the different shifts. So in different solvents, you would have a different shift to the reference.
This one.
Yes, exactly. So from my understanding, when you have a nanocrystal in a solvent, there's always some dissociation of the ligands that occurs just when it's in some solvent. And so there's some kind of a balance between like ligands that bind to the surface and ligands that like dissociate from the surface. And so I'd expect, or
that is not true. That is not true. That is true for some nanocrystals, but it really depends on nanocrystal ligand combination. In the case of cesium lead bromide with those oldyl ammonium ligands, they are really, really labile. So there it's impossible to get a monolayer of ligands on the surface. In case of carboxylates, that is often possible. So in the case of get selenide, in the case of hafnium oxide, it is really possible to purify well and remove all free ligands, and there's then one monolayer remaining on the surface. We can actually probe this because we would see this in dosing if there was a small fraction desorbing. You're right in the case of lead sulfide, for example. In toluene, everything is bound to the surface. But in chloroform and in dichloromethane, this lead oleate shell has a tendency of desorbing. So it really depends on the combination of nanocrystal, ligand, and solvent.
Okay. And so the reason why I don't see any cross-contamination in these graphs is because those ligand nanocrystal combinations just bind very well.
Yes. Have you noticed that in toluene I show quetzalnite, lead sulfide, and hafnium oxide?
Yes.
But not in chloroform? That is because
Yes.
I cannot trust the shift of lead sulfide or the line width of lead sulfide in chloroform.
Okay. Okay. Thank you.
You're welcome.
Okay, Aniket.
Oh, thanks, Jonathan, for the talk. I had a couple of questions. So the first one was on asymmetry, and I think on this slide, it's also a good indication. So do we already know why there is like this asymmetry for the peak, apart from just the broadening? Is there a reason for that, or?
That is a very, very interesting question that I don't know the full answer to. What I do know is that, let's go to this slide, it's actually better, that it has to do something with solvation. Because in toluene, this peak is asymmetric, and as soon as we add hexane, the peak becomes fully, perfectly symmetric. So it has to do with the solvation. Can it be that there is a difference in facets? That is a conjecture. That is possible, that some facets are better solvated than other facets in toluene, but that all facets are equally solvated in hexane. That could have something to do with how close the ligands are spaced. So that is a hypothesis, but that's not proven. The only thing that I know about this asymmetry is that you can remove it by choosing the right solvent. So it has to do something with solvation.
Okay. And then perhaps the second question was more on the aspects of ligand exchange of phosphonic acid with carboxylic acid. Firstly, does phosphonic acid bond exactly the same way as carboxylic acid does? And how does it like subsequently affect the optical properties?
Right, also a very good question. So that's why I went to this slide here. So we often, in a cartoon way, draw the carboxylic acid like this. This is most likely not the case. Most likely it is more binding like this. And that has been, well, confirmed. You cannot confirm a model with another model, but at least calculations are consistent with such a binding mode. In the case of phosphonic acid, yes, also there the phosphorus oxygen double bond almost most certainly participates. And then there are also reports that the second acidic moiety of the phosphonic acid can hydrogen bond to the neighbor. So that this is an additional stabilization of the ligand shell on the surface. What I've always noticed when I worked with semiconductor nanocrystals and phosphonic acids is that the quantum yield always went down.
Yeah.
And I don't understand that. But that is very consistent observation.
Okay, because presumably it would be the other way around, right? Because you're binding perhaps strongly, so you might perhaps, I don't know.
You don't know what you're doing exactly to the surface. So like I said, we don't have the spectroscopic tools to actually look at how the surface atoms are reorganized when you do a ligand exchange. The only thing what we can do is calculate it. If we think about Ivan Infante's hypothesis, where it's the two-coordinate selenium that is actually causing this trap state in the band gap, then maybe there is some way that the phosphonic acid causes that. I don't know. It's a good question, but it's hard to have the answer to that because we just don't have the spectroscopic tools.
Okay. All right, thanks a lot.
Okay, Nuri.
Oh, hi, Nuri.
Hey, Jonathan. Yeah. So we haven't talked for like a year or two. So first,
yes,
on the position, it's great to have you in the Swiss network.
Thank you.
After your visit. And yeah, thanks also for the great talk. So I had a question also about the first part that I was thinking about. I was wondering, like you kind of started hinting at it in the response, I think, to the first question. Do you have data or is there data which can kind of correlate absorption or desorption of ligands from the surface of the nanocrystal to the solvation of the ligand. So in a sense, if you fully solvate the ligand shell, is it possible that this could actually increase like desorption rate?
Yes, I think so. I think that's correct. What data is out there? There is the data from Carlo Giansante on lead sulfide. He has a paper clearly showing the trend from toluene to chloroform to benzene, to dichloromethane, that there's more and more desorption. It'll have something to do with the solubility of the lead oleates complex in that solvent. So when I think about ligand exchange, there are lots of parameters in there that play a role. One of them is binding affinity, but the other one is solubility. If you have two ligands, and you're trying to look at the competition with the surface, but one of them, and they have the same binding group, for example, but one of them has a lower solubility than the other one, then the one with the lowest solubility will bind to the surface because its chemical potential will be lowest there, and the one that is most soluble will have the lowest chemical potential in solution. So solubility really plays a role. And what you're asking is basically a desorption of the Z-type ligand. So this is the equilibrium nanocrystal plus Z, or nanocrystal Z, and then equilibrium arrow to nanocrystal plus Z. So that reaction is obviously also dependent on the solubility of the Z-type ligand. In the case of cadmium oleate and cadmium selenide, the binding affinity is so strong that the solubility does not play a role. But in the case of lead oleate, this binding affinity is rather weak, which means you can influence it with the solubility.
I see.
And then what we also have is data of more polar ligands. Oh yeah, actually I didn't tell you the full story here, but this is not a normal proton NMR spectrum. This is a diffusion filtered spectrum where we only selectively look at the bound ligands, because this ligand here has a solvent-dependent desorption. So while it is all bound to the nanocrystal in toluene, in an acetone 2 and in ethanol, you start to see a small peak of free mea. In methanol, there's a considerable amount of free mea, and in water, there's a lot. And so so you cannot just look at the 1D spectrum and say something about the line width, because it's a convolution of free and bound, which is why we had to do this diffusion filtered trick. But this is, I think, the most clear example of the answer to your question. Yeah.
So for kind of long-term stability, you may not actually want to go with the most soluble solvent, but
exactly,
maybe something in between. So
yeah,
kind of trade-off.
Definitely, that's right. Because don't be fooled in the sense that the colloidal stability in toluene is excellent. So it is not because the solvation is poor that also the solubility is poor.
Yeah, cool. Thanks.
Okay, Andrew.
Hey, great talk. So I had a quick question about the upconversion. So with the ligand coverage with the anthracene, did you guys do any studies on like varying the total coverage of it, or did you did? Okay. Did you see any change to the yield when you did that?
Yes. So basically, all the measurements were done at the concentration that gave the optimum quantum yield.
Okay.
So yeah, there was a series of different concentrations. Then the quantum yield was determined, and then we did everything with the sample that gave the highest.
Okay. And do you know like what ligand coverage that was with?
Very low. It was only a few per nanocrystal. Okay. I think maybe even 2.
Okay. Cool. Thanks.
Any other questions before I ask a question? So I wanted to go to the ODE again. I think this is super interesting, and of course, big value, I think, to the whole community to see that there's this problem. But in the end, so has it mattered? I mean, so clearly for TM, it's important. But has anybody, either you or somebody following up on your work, shown that this is relevant for transport or something like contamination that you can't get rid of?
Okay, you're pointing to a sore spot in the sense that this paper has been disappointingly not been cited. I was like, okay, now everybody will change the way they make nanocrystals, and apparently, well, not many people have done so, or at least reported it. So no, there are no follow-up studies that have shown this. I would suspect that having this polymer that is non-conductive around should have an influence on the transport. So I don't know the answer to your question.
But I guess it's also related to how much you can't get rid of, right? If with methyl acetate you can get rid of most of it. So I don't know what the answer to that is. So you studied that. So if you can if there's trace left after you purify them, and that's why we all spend all this effort, you know, trying to purify our nanocrystals and get rid of this organics, as you say. But now you know the source of this.
Okay, I have two answers to that, but I have to be very, very careful. The first one is that yes, I know of people that use methyl acetate as the non-solvent, and I've seen their NMR spectra, and it looks like they got rid of most of the polymerized octadecene. But I have also seen them purify it, and it's a painstaking way of doing it. So you have to be very careful. You have to do the exact right amount of methyl acetate to crash out your particles, but not the polymerized octadecene. And at the time they were optimizing this whole method, they didn't even know they were trying to separate the polymerized octadecene out. They just saw some stringy thing that they thought was cadmium molate. So yes, it is possible if you do this very carefully. But if you think about scaling this up or doing this quickly or more efficiently, then this is not really the right way. And the second answer I have is yes, I just remember one person telling me to see a very, very big difference in a certain application that has something to do with transport. But I don't think I am allowed to say much more. But okay. Yes, there was a very big influence.
I mean, I would assume it would have an impact. So I mean, it wasn't a negative question. It was just wondering if people have already seen this.
Impact, yeah.
Okay.
So yeah, one report. I know of one report that saw a difference.
Okay. Any last question? If not, I want to thank everybody for participating on this late Friday, and also especially Jonathan for giving us this very nice talk.
It was my pleasure.
Let's give him another round of applause or knocking. And with that, Jonathan, I'll send you the recording and you can use it as you wish. And
thanks a lot.
We'll have it here. So thank you, and have a good weekend, everybody.